Hi everyone, and welcome to another video for algorithms and data structures. In this one, we're going to keep looking at that big O thing and seeing what we can use it for. So we discussed big O in the last video, or rather, you saw me present it in a Collage-orama edit. Now, knowing how big O works, you should be able to figure out this one. So here's a function, it's called foo. It does some computation, and I wonder what is a bound, or which of these is a bound on the runtime. Give yourself 5 seconds, see if you can figure it out. Pause the video if you want. I'll continue now. So, in this example, there's actually 2 right answers. You see, what happens is there is this for loop over all the elements, so it's at least on, right? Every element needs to be operated on. That scales linearly. If I have twice as many elements, it will take me twice as long to go through the list. However, it's also bound by some function on squared. Why is that? Well, because any linear function is bound by a quadratic function. A quadratic function grows faster than a linear function after all. So after some point, it will be bound by this quadratic thing too. But that's not very useful, is it? Because that means that we could say for every algorithm, well, for many algorithms, that they're bound, for instance, by n to the power 200, or that they're bound by 2 to the power n. So what we would like is that we reason about the worst case and put a bound on that, and that bound is also tight. So it seems that just big O as a bound isn't good enough. We need other bounds too. So let's see if we can find some. How about a bound, for instance, that is a lower bound to our runtime? So we call this thing Big-Omega, Big-Omega, whatever your pronunciation of the Greek letter is. And you'll see that the definition is very, very similar to that of big O. Only we say that our function is larger than or equal to some constant times g of n. So for instance, a simple for loop that only iterates over a list of size n is lower bound by a linear function. So a function that iterates over a simple list of size n is omega n. So you might now think, okay, so that's great, but what can we use this big omega for then? Well, it suffers from the same issues as big O does, in that our simple for loop is also omega 1. It's also lower bound by some constant time function. So in practice then, this big omega isn't all that useful. There are some things for which we can prove a tight big omega bound, knowing that it at least requires this much time. For example, later on when we talk about sorting algorithms, we will learn that it has been proven that a comparison-based sorting algorithm requires at least n log n steps. So there is a tight omega bound on comparison-based sorting algorithms. But there's again that notion of tightness. As soon as we get to talking about at least this many steps, so at least n, knowing that it's more than constant work, then things start to become useful. And similar with big O, we saw that it was mostly useful as soon as we had this tight upper bound, as soon as we knew something was quadratic work but not cubic. So perhaps we can combine these two. What happens if something is both omega of fn as well as O of fn? Then interesting stuff starts to happen. And for this, we also have a special name. We call it Big-Theta. As soon as something is both lower and upper bound by a certain function, we say it's tightly bound by that function. It behaves as a quadratic or a linear function as n grows large. And that's great, because that's exactly what we've been looking for. So this big O, or this Big-Theta rather, is very useful. It offers a tight bound on the runtime. For example, when we look at our bit of code from before, this little for loop, we know that it is both upper and lower bound by some linear function. Therefore, we can say that this function is theta n. It is tightly bound by a linear function. All right, so 3 videos later, it seems like we can finally compare algorithms in terms of runtime. Or can we? Is this big theta, this big O, this big omega, is it really a good idea to use these? Maybe there's one more thing we should take a look at, and we'll do that in the next video.